Hello there again. This is the last video for chapter 2. So I'm going to finish chapter 2 in this video. So let's get started. I hope you're doing well. So this section is about the precise definition of a limit. We talked about what a limit actually means, and we know about the notation of limit. So limit of f of x when x approaches a equals to L, that's how we write it. But what does that mean exactly, and how do we prove it? Now, to prove this, here's what you have to do. So if you have a function whose limit at a is L, if I want to prove to you, for example, that the limit of this function is a, then I'm going to have to be able to do this. If you come up with any epsilon distance from L, and epsilon is just a small positive number, so if you want to be within epsilon of L, then I'm supposed to be able to find a delta here. Delta also is a small positive number, such that if x values are between a minus delta and a plus delta, then the y values will stay within this distance, which is epsilon unit from L, right? So if I can find a delta that satisfies this for every epsilon that you come up with, then I have proved that the limit is L. That's how we prove it. Now, of course, we have to talk about this. So let's just start by translating this kind of official mathematical language to English, okay? So let's do that first. So for every epsilon greater than 0 means that for every positive distance epsilon from L. That means if this is L on the y-axis, we are talking about for every positive distance epsilon from L, there exists a delta greater than 0. There is a positive distance delta from A. So if this is A, there is a positive distance from A such that, which is English, this is true. Now, what is this? This is an if statement. It says that if this is true, then this is true, right? So what does that mean? It means that if you are in this interval on the x-axis, then the y values are in this interval on the y-axis. So of course we're going to talk about this, but that's the idea. All right, so let's talk more about that absolute value notation because we use it in this definition. So let's talk about what this means. So when we write absolute value of a number minus another number, by that we mean the distance between the two numbers. That's all it means. So if the two numbers are on the x-axis, it means the distance between the two numbers on the x-axis. If the two numbers are on the y-axis, then that means the distance between the two numbers on the y-axis. So here are some examples. These are obvious. What does this mean? Absolute value of 10 minus 6. It means the distance between 6 and 10 on the number line. So here's 6 and here's 10. That's the distance between 6 and 10. Now if the 6 and 10 are on the y-axis, then that means the same thing. It means the distance between 6 and 10. And this is the same thing, distance between 6 and 10, this distance between 10 and 6. Here it means the distance between negative 6 and 10. And this means the distance between some number and 10. But of course this number could be any number that works, right? So when we have something like that in algebra, you learn how to solve it. When we say x minus 10 equals to, absolute value of x minus 10 equals to 5, By that we mean numbers whose distance from 10 is equal to 5. And where are those numbers whose distance from 10 equals to 5? Well, those numbers are between, there are either 15 or 5, right? So how do we know it's 15 and 5? Well, because there's a distance from 15 to 10 is 5, and the distance from 5 to 10 is also 5. How do we solve this? Well, you learn in algebra that how to solve that, right? So you can solve that easily using equation like this, right? You learn that in algebra, and then you solve them and you get 15 and 5. But more importantly, we're going to talk about this last two, especially this one, because the definition uses it. So what we want to do is we want to talk about what this means. What this means, we're looking for numbers whose distance from 10 is less than or equal to 5. Where are those numbers? Well, we know that 15 and 5, of course, are two of them. But then any other number between 5 and 15 also works, right? Because if you pick this number here, the distance from this number to 10 is less than 5, right? Any of these numbers will work. Now, more importantly, what we mean by this is this, that x minus 10 is between 5 and negative 5. Or the number we're looking for is going to be between 10 plus 5, right? And 10 minus 5. Basically add 10 to all sides, right? That's what it means. So when I write x minus a absolute value is less than epsilon, what do I mean? I mean that x minus a is between negative epsilon, and x is between a plus epsilon and a minus epsilon. That's exactly what we talked about, right? This interval from to the left and right of a, that's that interval right here. So instead of writing all that, we just compactly, we write absolute value of x minus a is less than epsilon, okay? Now when we write f of x minus L, absolute value less than epsilon, what is, I should have said delta, I said epsilon. So let me redo that. So when I say x minus a is less than delta, I mean that x minus a is between delta and negative delta. And so x is less than a plus delta and a minus delta. Now over here we mean that f of x minus L is between epsilon and negative epsilon. So f of x is between L plus epsilon and L minus epsilon. So remember, epsilon is on the y, delta is on the x-axis, okay? All right, now what do we mean when we say that absolute value of x minus 10 is greater than or equal to 5? Well, we mean that either x minus 10 is greater than 5 or x minus 10 is less than negative 5. So basically on the number line, this is 10, then this is 15, this is 5. So what we mean by this is that we're looking for numbers whose distance from 10 is greater than 5 or equal to 5. So those numbers are 5 and 15, or any number greater than 15, right? Erased it accidentally. And any number less than 5, right? So that's the idea. Of course, in algebra, you learn that to solve such an inequality, that's what you do. And then solve the inequalities separately, put them on the same number line, and that's what you're going to get. All right, now that we understand the language used in this definition, and I just talked about this, f of x minus L, absolute value less than epsilon, what it means, and absolute value of x minus A less than delta, what that means. Now here we put greater than 0 to indicate that when we approach A from right and left, we don't want to be A actually, right? We want to approach A. We don't want to be A. So that's why we put that greater than 0 here. All right. So here is an example. Suppose we have limit of x squared equals to 9 when x approaches 3. How do we write the definition for this? Well, we always start with this. We start with, for every epsilon greater than 0, there is a delta greater than 0 such that, well, here f of x is x squared and L is 9, right? Now we have two choices for the second part. We can either write, you see we have, the second part is if, the statement is if A, then B, right? In math, if you have a statement like this, it's a conditional statement. It's a one-way statement. If A, then B. So instead of writing it this way, we could also write it this way. B, so this says if A is true, then B is true. Now we can write it this way. We say B is true, right? Whenever A. So that means B is true whenever A is true. That's exactly saying the same thing. If A is true, then B is true, right? So these two statements are equivalent in math. Sometimes you see in some textbooks, they write it this way. And so we have to understand that. But usually we write it the first way, this way, to prove it. So we're going to write it for this function. So we're going to write it for limit of x squared when x approaches 3 equals to 9. So for every epsilon greater than 0, there exists a delta greater than 0 such that if x is within delta of 3 on the x-axis, right? That's basically what it means. If x is here between 3 plus delta and 3 minus delta, but we write that this way. If this, then what? Then f of x, which is the function values, are going to be between what? Are going to be epsilon unit from 9. So it would be between 9 plus epsilon and 9 minus epsilon, and we write that this way. So that's the statement of the proof. That's how we write it. Of course, we still have to prove it, right? But that's how you write it. And here's another example. How do we write it? Again, we write for every epsilon greater than 0, there exists a delta greater than 0 such that if. So this right here is our x minus A, right? Looks like that. So instead of A, we have to put negative 1. So if I put negative 1 here, it would be x minus negative 1, which is x plus 1. And this statement here is f of x minus L less than epsilon. And here, instead of f of x, we put that. And instead of L, we put negative 4. But the minus is there because it's part of the formula. Less than epsilon. That's it. All right, so let's prove one of these. How do we do that? Well, first we write the statement. The statement says what? The statement says that limit of 2x plus 1 when x approaches 1 equals to 3 if for every epsilon greater than 0 there is a delta greater than 0 such that if this is true, then this is true, right? Now, first of all, let me talk about a common mistake which students make, and that is when I give them something like that to prove, they say, well, this is easy. Just substitute 1 and you see the limit is 3. Well, that's not what we mean by this, right? we mean prove it using the limit, the precise definition of limit, not using substitution. All right, so we have to actually prove this. Now to prove this, we can either start from left and say, if we have this, then we're going to have that. But that's kind of hard to do because you see, you don't have enough material to work with here. Here you have more materials to work with. So what we do, instead of starting from this and coming up with that, we're going to start with this and get this out of it. Okay, so we're going to do this. So let's do that. So first we write this statement. We write, let x be greater than, let epsilon be greater than 0, period. Choose delta to be, we don't know yet what it should be, but we're going to put this here. We choose delta to be, we don't know, put period. Okay? Okay, now, instead of writing if this, then that, I'm going to write this first and then get this out of it. Right? So I'm going to start with, so what we're going to do is this, if x minus 1, remember that's our a here, is less than delta, then what's our f of x? 2x plus 1 minus, what's our L? 3. Less than epsilon, right? So instead of starting from here and prove that, I'm going to start from here and go backwards, right? And then these arrows, I'm going to make them two-way because what I do here can be reversed, right? So I'm just going to make them double arrows. So if absolute value of 2x plus 1 minus 3 is less than epsilon, then if we simplify, 2x minus 2 is less than epsilon, absolute value of 2x minus 2 is less than epsilon, then we know because of that we can factor the 2 out. So we have 2 times absolute value of x minus 1 is less than epsilon. You see, we have to keep an eye on this right here, this part, because we're trying to what? We're trying to get that out of what? Out of that expression. So we simplify this and see if we can get this out of it. All right, so it looks like we kind of got it, because if we divide both sides by 2, we get it. You see this right here. That now you compare it to what? To this part. And you see that if you let delta be epsilon over 2, so if I start with this idea, if I put epsilon over 2 here, then I can get this. Why? Because remember what we just did. We started with this and we got that. And every step is two-way step, right? Every step I took is a two-way path that I can go back. So if I can go backwards this way, then I can go forward this way and get this too, right? So that's the idea. So what we're going to do now, we're going to write that. We write, let epsilon be greater than 0, choose delta to be epsilon over 2, period. Given this, we have this, right? How do we know that? Because we just proved it. Because we started with this and went backwards and we got that. So we could go forward and get this, right? So that's the idea of how to prove this. Now sometimes instead of proving it, we just want to find one delta for a given epsilon. So in this example, we're given a picture of this limit. Limit of f of x when x approaches 2 is 4. So we are given 2 examples of epsilon. 1. So if I want to prove this to you, and you say, okay, I want my epsilon to be 1, give me a delta. Then I go to the graph and I say, okay, here is my L, the limit. So I want to go epsilon to the epsilon above it and epsilon below it. So that would be 5 and 3. epsilon is 1, right? Now from 5 I go to the graph and then go down to x-axis, and from 3 I go to the graph and I go to x-axis, so I hit 3 and I hit 1. Now what is my delta? Well, notice that the distance from 2 to 3 is what? Is 1 unit, and the distance from 2 to 1 is 1 unit, so my delta is 1. So delta here is 1. Now what if you change your mind and say, okay, I want epsilon to be 1/2. Then I'm going to do the same thing here. I'm going to go to what? I'm going to go to my L, which is 4, and go half a unit up and half a unit below it. And then I'm going to go to the graph and go down. Oops, right here. It was a little crooked, but and go there. So that's like 1.5 and 2.5. So it looks like go 0.5 to the right and 0.5 to the left of 2. We can get that interval. So delta is 0.5. Okay? So delta is 0.5. Okay? All right. The interval around x on the x-axis that guarantees f of x will be within epsilon of L is not always symmetric. That means whenever we find delta, the interval here, let's say we have a function, right? And then when you do, L plus epsilon and L minus epsilon, and you go to the function and you want to find your delta, the interval that you find around A is not always symmetric. That means the distance here could be smaller than distance here. But what is your delta if that's the case? Well, the delta would be the smaller one. Because if you pick the bigger one to be delta, then you're going to have to also go that much to the right, and then you don't hit the interval that you're supposed to hit here with the y value, right? So the y value goes above the interval L minus epsilon and L plus epsilon. So whenever the interval is not symmetric, we pick the smaller distance to be our delta. Okay, so we have an example here. Let g of x be this, and given that limit is 2 when x approaches 1, use a calculator to find the delta for epsilon equals to 0.21. So we want epsilon to be 0.21, and the limit is 2, and then a that x approaches is 1, right? So how do we do this? Well, let's use a calculator. So what I'm going to do, I'm going to put the function in the calculator, x to the third minus 5x plus 6. And in y2 and y1, I'm going to put L plus epsilon and L minus epsilon. Remember, L was 2, right? So I'm going to put 2 plus epsilon, which was 0.21. Remember, we're supposed to use 0.21. So that's 2 plus 2.21, which is 2.21, but you could just put it like that. And then 2 minus what? 0.21, right? That's it. And then I'm going to go to window and make sure that I have enough room for x and y values. So x values here go to, it's from 1, right? X values is from 1 because the limit is what? Is around 1. So I'm going to make sure 0 to 3 is good for that. And then I'm going to go to y values, y min and y max. Well, notice that our y min and max should include these values here, 2.21 and 1.79, right? So what I'm going to do is I go from maybe I don't know, 1 to 5 is good. Yeah, I think it's good. Yeah. So here you go. So that's the function. Here is my L minus epsilon, and that's my L plus epsilon, right? So how do I find the x values? Well, I can use the calculator to find what? To find this intersection and this intersection. The way you do it is you go to second, calculate, intersection, which is number 5. And then you have to give the calculator 2 curves to find the intersection of. One of them, of course, is the graph. So we could go arrow up and arrow down to go between the functions, right? You see that? So right now, where am I? I'm on the function. So that's a good one. So I'm going to pick it, press enter. Now my second curve, I want to be on that line right here. And I want to just make sure I'm on that line and press enter. Then it says yes, we want to be close to what? That intersection, because there are 2 intersections. I want this one. I'm not interested in this one because this one is not around 1. This one is around 1. So I'm going to move the cursor closer to the intersection and press enter. So you see right here, that's one of my intersections. So I have it right here already. See? So I'm going to write it down. And then the other one is here. So I'm going to do this again. Second, calculate, number 5. And then again, where am I? I'm on the curve, so press enter. Now I want to be on the line below it. Am I on the line below it? Yes, enter. And then I want to be close to the intersection on the left, that one right there. I want to put it there and press enter. There, 1.13. So I put it right there. See, I wrote it down. So what I want now is my delta. Now notice if I go to the left, 1 is in the middle here, 1 is here. If I go to the left to 0.90745,149, the difference is 0.09. If I go to the right, which is this x value, right? See, I can move the y min below the x-axis so you can see it right here. Let me do that. So you see my 1 is right here, right? And here is to the left and to the right of 1. So to the right we have what? The difference between 1.13, 24956 and 1, and that's 0.13. So it looks like the interval is not symmetric, right? So here's 1, and then we got 1.13, and then we got what? 0.9 something. The difference here is 0.13. The difference here is like 0.09. So which one is delta? Well, it's the smaller one. We're going to pick the smaller one to be delta, right? So our delta would be a smaller one, and the reason, of course, is that if we pick the bigger one, it wouldn't work. So I'm going to show you why. So here for 0.21 epsilon, we pick delta to be what? To be 0.09, because this is smaller than 0.13. Now here is the same problem, but I want to take you to this animation, and you can see. Oops. Let me show you. There you go. So again, I use the GeoGebra to do this. And now here, here is different values of epsilon. For different values of epsilon, you can actually find different values of delta. Now what I have here, you see, this is epsilon. So if I pick epsilon to be, let's say, about 0.21, see if I can make it 0.21. Here we go, 0.21. That's the number we found. And notice that there are two deltas here, 0.09 and 0.13. If I pick delta to be 0.09, right, what happens? Well, if I pick it to be 0.09, my interval on the y-axis is going to be right here. So if I pick 0.09, my interval would be 1.84, 2.21. Now remember, L plus epsilon and L minus epsilon is this interval here. So my y values have to be here for this thing to work, right? Now here you see the blue band, right? Right here, the blue band is based on smaller alpha, which is 0.09. You see, I went to the left and to the right of 1 here, 0.01, 0.09, and then here's the y value right here, and then I went to the left of it, 0.09, and here is the y value right there. So you see, this is 2, so I am within what? In this interval, and this interval is right here, which is what? Which is inside this interval that's supposed to be, right? The right end are the same, but the left end is inside, right? But if I pick delta to be 0.13, notice that this goes outside of 2.21. You see that? And that's the red band right there. The red band is based on picking delta to be the bigger one, and you get that red one. All right? So for different values here, for delta, you see that there are two different values for epsilon, there are two different values for delta, and we always have to pick the smaller one, right? All right, so that's the animation that would work. So let me go back here. So, and I explained this right here. You can stop the video and look at it, right? The same thing I just described is right here. You can click on this image in the notes. You can click on this image and open that GeoGebra file and play with it just like I did. All right. So here is another example, and I'm going to let you do this. Let me wait on it for a few seconds. You can stop the video, get your calculator, and do this one. It's exactly like the one I just did, except that the interval is pretty symmetric, so you don't have to pick the smaller one. They're both about 0.42. But go ahead and stop the video and use your calculator and this new function and see if you can find a delta for epsilon equal to 1. Here's the limit is 24. So what you have to put here is 24 plus 1 and 24 minus 1. And then that's what the graph, that's what you get. You find the intersection, find the x values, find the difference, and you get it. So I'm going to skip this one, let you do it. And here's another one. So it says find the delta when epsilon is 0.25 for this limit, right? So here's what we do. So let epsilon be 0.25, choose delta to be 0.5. Given that, we have that. Now, how do we know the delta is 0.5? Well, we can find it. Here we go. So we say let epsilon be greater than 0, choose delta to be, well, we don't know. So here is our epsilon is 0.25. So we say let epsilon be 0.25, right? So we put it there. We start with what? We start with this expression that f of x minus, this is our f of x, right? Minus what? Minus 2. How do we know limit is 2? Because of what we're given here, right? We're not explicitly given the limit, but we know what the limit is because of what? Because of that. So let me explain what I mean. So because of this, and because of this, we know this is the limit of x squared minus 2x plus 3 when x approaches 1. How do I know? From here. Is 2. How do I know is 2? It's because of that. Okay? So basically we want to prove this only if when epsilon equals to 0.25. So we start with this expression, which is basically what? Is this minus what? Minus 2, right? Right here. Simplify it more. This is just x minus 1 squared, right? And since this is positive, we can just remove the absolute value. And since they're both positive, we can take square root of both sides. And we know square root of x minus 1 squared is absolute value of x minus 1. And less than square root of 0.25. And now you compare this to what we have here, right? And you see that delta has to be what? Square root of 0.25. And that's how we know this. So if you let delta be 0.25, right? 0.5. So if you're on the x-axis and here is 1, if you go to the right and left of 1, 0.5, then on the y-axis, if this is 2, then on the y-axis you stay within what? Within 0.25 of 2. So y values would be between 2.25 and 1.75, right? So basically, if you stay within 0.5 of 1, y values will stay within 0.25 of 2. Now, we could also do this problem in general, just find any epsilon. If you come up with any epsilon, I could find the delta for you. So instead of doing this for every epsilon you give me, I'm just going to let epsilon be epsilon. Instead of being 0.25, I just let it be epsilon, right? Then I go through the same procedure. And notice I get what? I get again something that looks like that. So I know my delta has to be square root of what? Square root of epsilon. And the square root of epsilon works all the time. So whatever epsilon you give me, I just take square root of it and use the delta, equal to square root of epsilon. Okay, so I write let epsilon be greater than 0, choose delta to be square root of epsilon. Then every time you have this on the x-axis, you will have this on the y-axis. Make sense? So on the x-axis, if you are square root of epsilon to the right and to the left, then on the y-axis you will be epsilon from 2. That's the idea. If you are within a square root of epsilon here, a square root of epsilon here, then you would be within epsilon here and here. Okay? All right. So here is another one. It says prove this limit. Okay, so we start with the same kind of idea. We say let delta be, well, here's the trick here. The problem with this is we have to write if absolute value of x minus 2 is less than delta, then what? Then absolute value of x squared minus 2x plus 3 minus 3 is less than what? Epsilon. Now the trick here in this problem is that when we try to simplify this, we're not going to be able to isolate this out of it easily. And you see it right here. So if we try to do that, what happens is this, you see? So if we try to, so let me do it here. So what do we get? Well, 3 and 3 cancel, right? So what we have here is x squared minus 2x is less than epsilon. And then if we factor this, it would be x times x minus 2 absolute value less than epsilon. And this would mean that absolute value of x times absolute value of x minus 2 is less than epsilon. Now notice this is not similar to the one that we just did. In what sense? In the sense that we cannot isolate x minus 2 out of it, so we can compare it to this and see what epsilon is, right? What delta is. So what we have to do, we have to get rid of that somehow. And to do that, we use this trick here, okay? So we let delta be less than or equal to 1. Now obviously for some epsilon values this delta will work, right? So we just let it be less than or equal to 1. You can pick 2 or 3 or whatever positive number you like. You just try one delta, and we know that delta will work for some epsilon values. So let it be less than or equal to 1. So that means if we are within 1 unit on the x-axis, if we are within 1 unit of 2, right, then x minus 2 absolute value less than delta becomes absolute value of x minus 2 less than 1, right? And that would mean what? That would mean that x minus 2 is between 1 and negative 1. And that means that x is between 1 and 3. You just solve for it, right? Now, if x is between 1 and 3, then absolute value of x will be less than 3 for sure, because all the values x can take are from 1 to 3, and then absolute value of x will be between 1 and absolute value of 1 and an absolute value of 3, which is basically the maximum it could be is 3, right? So we're going to go back here in this problem that we had. So we're going to go back here and say, okay, instead of absolute value of x, I want absolute value of x times this to be less than epsilon. So I'm going to make absolute value of x as big as it could be, which is 3. So I've just put a 3 there. Now I can isolate x minus 2, right? And now I compare this to this, and I see that my delta has to be what? Epsilon over 3. But here we have a problem, right? Because we got this from the fact that delta is less than or equal to 1, right? So that means delta will work for some values of epsilon. For what values of epsilon? Well, remember, if we pick a delta, anything is smaller than that works too, right? So if delta equal to 1 works, then any value of delta less than 1 will work as well. So what we do here, we say, okay, if epsilon is anything greater than 3, so if epsilon is, let's say, if epsilon is 3, 3 over 3 is 1, and that's the delta we already have. If epsilon is 4, then 4 over 3 is 1 and 1/3. So we're going to pick 1 because 1 already works, right? 1 is smaller than what? 1 and 1/3. So 1 works. Now, the problem is that when somebody, let's say, I want to prove it to you, and you pick epsilon to be 2, then 2/3 is smaller than 1 that I started with. So I have to switch my choice and say, okay, I'll let delta be 2/3 this time, right? So in this kind of situations, when we use this trick to get rid of part of this that we couldn't get rid of, we have to write this. We have to write that delta is minimum of either 1 that I started with or this expression. So that means if epsilon is, let's say, 2 less than 3, then I'm going to pick this to be delta. And if epsilon is greater than 3 or 3, then doesn't matter, I can pick 1, right? So this means that pick the smaller of the two numbers. So when we write delta is minimum of 1 or epsilon over 3, that means pick the smaller one, right? That's it. That's how we deal with this. So this is what we're going to do. So write the proof. We write let epsilon be greater than 0. Choose, that means for any epsilon, choose delta to be minimum of these two. Then, given this, we have this. Right? Depending on what epsilon we have, we can pick a right delta here. And based on that, we prove that the limit of this thing when x approaches 2 is 3. Right? All right, so here is the, again, I'm going to, in the notes, you can click on this and it takes you to GeoGebra Online, to my account online, and you can use this. So what I did here, I created that, and you see that, so you can work with this and put different values of epsilon and delta. You can change the values of epsilon and delta and see this is epsilon and then this is delta, and see how the value, how that band changes. See, this is the band changes for every value of delta. So it's that problem, and if we pick epsilon to be let's say 4 and let delta to be 1, right, and that would be the band, right? So this didn't load the other two lines somehow. See if I can reload it, it might show up, but it's just something you can play with. It didn't load, but no, it didn't load. Okay, so let me go back. So that's, you can play with, and for different values of, so over here you see the band that I wanted to show you. You see, this is L plus epsilon, the blue one, and this is L minus epsilon. So if I pick epsilon to be 5.8 and delta to be 1.1, right? Does that work? Yes, right? That works. Why? Because the band, the red band, has to be within the blue band, right? Now online, the blue ones somehow didn't show up, but if they show, then you can see whether your delta works or doesn't work. In this case, it does work, right? So if I can delta to be 1.1 with the epsilon 5.8, it does work, because you see, I satisfy the statement of the proof. All right, so, and I wrote that already. So here is another proof. Prove this limit. Now this is very similar, but notice that x approaches 0 here, right? So again, we let, this is another problem when we're gonna, it's the same problem. So we're gonna have what? We're gonna have absolute value of x times absolute value of x minus 2, less than epsilon. And we're not going to be able to get rid of it if we don't use this trick. So again, we start with this idea that, looking for my pen, here we go. So again, here we have to write what? We have to write if absolute value of x, in this case, is minus 0, right? Minus 0 is less than delta, then absolute value of f of x, which is x squared minus 2x plus 3 minus 3 is less than epsilon, right? So if you start from here, we want to get that out of it, which is, by the way, x minus 0 is just x. So this is really absolute value of x less than delta, right? So if we want to get this out of here, if we set it up, we get what? We get absolute value of x, because 3 and 3 cancel. So we end up with x squared minus 2x again, which is absolute value of x times x minus 2, right? So we get that. Now notice again, we're not going to be able to get that. This is what we want. We want absolute value of x by itself. What do we have on our way is absolute value of x minus 2. We have to get rid of that. Now to get rid of it, we use the same trick. We say let delta be less than or equal to 1. If delta is less than or equal to 1, then absolute value of x is less than 1. That means x is between 1 and negative 1. And if x is between negative 1 and 1, then what is x minus 2? Well, just subtract minus 2 from all sides. What do we get? We get this. That means x minus 2 will be between negative 3 and negative 1. If x minus 2 is between negative 3 and negative 1, where is absolute value of x minus 2? Well, absolute value of x minus 2 would be between absolute value of this and absolute value of this, which will be between 1 and what? 3. That means the maximum value of x minus 2 absolute value would be 3. Again, we come over here and we say, okay, we want this times this to be less than epsilon, so let this be the maximum it could be, which is 3. So 3 times absolute value of x is less than epsilon, so absolute value of x has to be epsilon over 3, right? And now we compare it to what? To this, right here. If you compare that, you see that your delta has to be epsilon over 3. But, again, it depends, because remember, we started with delta equal to 1, right? So if we get whatever value of epsilon, should we stick to our value of delta? No. So delta is 1 or epsilon over 3 if this one is smaller, right? So again, we're going to let delta be minimum of what? 1 or epsilon over 3. Now notice that you don't have to start with 1. You can say let delta be 2. Then you take that into account here in your calculations, then you're going to get two different things here. But still, you can get the correct delta out of it given a given epsilon, right? All right. So this is what we want to write for this problem. We choose delta to be minimum of these two. Again, given this, then this is true. All right. All right, so I'm going to just talk about more examples where the limit is not just two-sided limit, it could be one-sided. So if it's one-sided, then on the x-axis, we're not interested to go to the left. This is right side. So we're not interested to be over here. We want to be over here. So that means on the x-axis, we want to be between a and a plus what? Delta. We don't want to be on this side. So instead of writing if absolute value of x minus a is less than delta, we're going to write it this way because we don't want to be to the left of it. We just want to be to the right of it. So this is how we write it. We say if this, then the y value is the same. The y value is the same. It doesn't change, right? So y values have to be within epsilon of L. And here's an example where the limit, of course, is the right limit. Limit of the square root of x when x approaches 0 from right is 0. And to prove it, we have to write it this way. Why? Because it doesn't make sense to go to the left of 0 here. There's nothing there. It's not defined there, right? So that's an example of how to write the statement of the proof for a right limit. What about a left limit? Well, for a left limit, again, here's a, right? So we don't want to be over here, so we want to be between a and what? And a minus delta. You can write it this way, or you can just write a x between a minus delta and a and 0 and a, like that. Or you can write it this way, that's correct too. Okay? Then the y values are still, within epsilon of L. And here's an example of a left limit. This function is only defined for negative numbers, so you don't want to go to the right of 0, right? So you write it this way. And I did it this way here. All right. Now, what about infinite limits? What if the function goes to infinity? Well, we can also write definitions this way. If x approaches a, left and right, and the function goes to infinity, well, here we can write on the x-axis, it's the same thing because we are going around a, right? So it's the same thing on the x-axis. So we write if this, then, but on the y-axis, we don't really have a limit to go around. What we have, it goes to infinity. So what we write is this, then f of x is greater than some number, right? So for every m that somebody comes up with, we have to be able to find a delta that works. What does that mean? That means if we are within that delta, right, then the y values would be greater than that number that we come up with. So that's how we write the definition of the limit. Precise definition of this limit is given here, right? So for every m, if I want to prove to you that this limit is infinity, then you say, okay, if I pick any large number, you have to be able to give me a delta such that if I'm within that delta, then the y values will be what? Greater than m. And it is, you see. If I pick this number here, which is within my delta, if I go up, you see the y value now is bigger than what? Is bigger than m, right? And this happens actually anywhere within my interval of delta to the right and to the left of my a, which is 0 in this case, right? So that's the idea. And here is the negative infinity idea. So again, on the x-axis, it doesn't change. It's still, we're talking about if absolute value of x minus a less than delta. But what has to be true is that if I want to prove that the limit is negative infinity, then you can come up with, for every number you come up with that is really, really large negative, I have to be able to come up with a delta such that it puts all the y values below what? So the y value for this would be that much, which is smaller than what? Smaller than m, right? And m is a, I should put negative m here, but there you go, right? If m is positive, we can assume m is negative and write it that way. So if m is a positive number, then we want to be f of x to be smaller than what? Negative m, because the limit goes to negative infinity. All right, and here is an example for when x goes to infinity. So what's the limit of f of x when x approaches negative infinity? Well, here is L, right? And so how do we write this? But, well, here on the x is not the same thing, because on the x we don't have an a. X goes to negative infinity, right? But on the y we have the same thing. So the y part of the definition remains the same, but the x part we modify into what? Such that if, instead of saying if x minus a is less than delta, we don't have that anymore. We say if x is less than n, then the function values are within epsilon of L. And I have an example here for you, right? Here's an example of a function that whose is 1 over x, the function. So this is a limit of 1 over x. When x approaches negative infinity is 0, right? So this is 1 over x, and the limit of it, so limit of 1 over x when x approaches negative infinity is 0. So if you want to prove this, then you, for every really negative number that you come up with, let's say you come up with this big negative number n, right? I have to be able to find a delta here around what? I have to find epsilon, right? For every epsilon you come up with, I have to find an n. I said it the other way around. So for every epsilon you come up with, if I want to prove that the limit is 0, for every epsilon you come up with around 0, let's say you want to be below 0 about 0.05, right? So if your epsilon is 0.05, I have to be able to what? To find a number here, which is a big negative number, such that, right? So I have to be able to find a number such that if I go after that number, right? After, I mean to the left of it, if I go even further to infinity after that number, the function values will stay what? Within epsilon of 0, would be inside this little interval here. That's the idea. Okay? So that's my limit, and here's an example. Again, x goes to negative infinity and y approaches what? A limit. We could also have a positive one. There you go. Now we can prove this. How do we prove that limit of 1 over x equals to 0 when x approaches negative infinity? Well, we're going to start with what? We're going to say, okay, let n be, or we don't know what it is because we have to find it. So let n be, and then period, and then given n is a big negative number, we have that this is less than epsilon, right? So we want to prove this. To prove this, we have to find n for every epsilon. So we start with this side, 1 over absolute value of x is less than epsilon, and then we try to get this out of it, right? So we want to try to get what? To get this out of it, x less than n. So how do we do that? Well, look, if we flip them, 1 over absolute value of x, we flip 1 over epsilon, we flip epsilon, and looks like since we're going to negative infinity and absolute value of negative is positive, we could just write it as x greater than 1 over epsilon, right? And then this now, x goes to negative infinity, so x has to be, because x approaches negative values, so we're going to say x be less than what? Negative 1 over e. We get this expression, but of course, we want it to be what? X less than n. This is x greater than 1 over e. How do we make it, less than n? We know x is negative, so that means x is less than negative 1 over e, right? So when x is negative, absolute value is actually negative x. Let's put it this way, right? Here you go. So let's put a negative here to correct it. And then we multiply by negative and we get this, right? So now this looks like what? This looks like this. And we let n be what? Negative 1 over e. So we complete our proof. We say n has to be negative 1 over e, and given x is less than n, then this is true. Okay? All right. Now, here is again another example. It says prove that a limit of 10 over x equals to 0 when x approaches infinity. In this case, x approaches positive infinity. So when we set this up, the y part of the definition of limit stays the same, f of x minus L less than epsilon. But the x part changes. How? This time we have to find a big number n, right, for every epsilon we are given, such that after that number n, whatever number we pick, the y values will be within what? I'm going within this epsilon. So it's going to be like this epsilon is really small, but see, after that, the y values stay within what? Within epsilon of that L. In this case, L is 0. And again, we write it this way. Let n be a number we don't know. Given x is greater than n, we have that f of x minus 0 is less than epsilon. So we start with that. And remember, we're trying to get this out of it. So this means that 10 over x is between, epsilon and negative epsilon. But we know 10 over x is positive because x is approaching positive infinity. So that means 10 over x is less than epsilon. If you flip both sides, we can flip the inequality, right? They're both positive. So x over 10 is greater than 1 over e. So we multiply both sides by 10. So x is greater than 10 over e. So now compare this to that, right? And we see that our n has to be 10 over e, right? So our proof is that let n be 10 over e, given that x is greater than n, f of x remains within epsilon of 0. And here's an example of n. If epsilon is 0.05, then n is 20. For every epsilon, we can find an n. After n, all the function values stay within 0.05 of 0. All right, so now here is a link. If you click on it in the notes, it takes you to a website. Actually, is a bunch of problems from University of California, Davis. They have good number of problems of proving. Some of them are tricky, actually. So I wanted to, if in case you're majoring in math or you're interested, you can look at the rest of these problems and see how they're done. I gave you some examples, but these are even more examples. And that's how you can get good at this if you're interested. But for our purpose here in this course, the examples that I covered, I think is good enough. All right, so this looks like the end of this video. So I'm gonna stop here and come back and say bye to you. Take care of yourself and others. I'll see you in the next video.